Okay, welcome to the Numbers Colloquium. Today we're very happy to have Elon Lindenstrauss tell us about new effective results regarding the Oppenheim Conjecture and polynomial effective distribution.
Thank you. So let's start with the quadratic form. Just over the real numbers. And what the subject matter, this is a quadratic form in the variables, and the subject matter of my talk is what can you say about, or what can be said about the set of numbers where you plug into this quadratic form an integer. And this is the general question I would like to talk about today. Now, I'm going to mostly talk about the indefinite case, but let's start with the definite case. If Q is, let's say, positive definite, then seemingly everything is very simple. Then for every then Q with the integers is discrete, not as discrete. Anyway, it's a discrete multiset. I'm sort of I care if something appears twice, I care about that. And I can write the set. So I can write it as 0 is certainly there, and I'm assuming without saying it that all my quadratic forms are not degenerate. So 0 is so for a positive definite form, 0 appears only once. So there is, and then there's lambda 1, lambda 2, etc. And with the lambda I, lambda n going to infinity, in fact, it's easy to see that that the nth term in this would be roughly some constant, depending on q, lambda to the 2 over d. So in particular, if you plug for
Okay, good.
In particular, if you plug in for d equals 2, then lambda n plus 1 minus lambda n is on average something like 1. If q happens to be rational in the sense, in the projective sense. If q is rational in projective sense, that is to say, I can multiply it by some real numbers so that now it becomes, all the coefficients become integers. Then obviously lambda n plus 1 minus lambda n is either bigger than this constant I was multiplying with, or equal to 0. Either way, in the case of the either way, for d equals 2, what is certainly true is that the Lim-Schuk of lambda n plus 1 minus lambda n is bigger than some constant. And maybe just say bigger than 3. So this is what happens for d equals 2. for the conjecture, which is known as the Davenport-Lewis conjecture, but I'm not quite sure why. I mean, they certainly considered it, but it would seem to me that it was considered way earlier. But anyway, it's a sort of conjecture that for D at least 3, if Q is irrational, in the same sense as before, then actually the gaps tend to 0. That's an open, that's sort of an obvious thing. And obviously requiring that the form be irrational is essential for it to be true. It's wide open for D equals 3. Can't say much about it. For D equals 5, so for the case of diagonal forms, this was proved by Yarnik classical theorem in the 1920s. For general quadratic form, this is a surprisingly recent fact. It's a theorem of Gutze. From 2000.
That is, the conjecture is true.
The conjecture is true. So for D equals 5, it's no longer a conjecture, it's a theorem. But for D 3 or 4, it's wide open.
Why 5? What makes things work?
Basically 5 is sort of where the circle method starts to work. So that's probably explicitly what Jarnik did, and a bit hidden because sort of he talks about theta functions, but basically also in Gutze's work. Now, how the basic method, so sort of the basic approach in both cases, and the natural approach, it's just count the number of, try to use the notations in my notes, so I'm try to count the number of lambdas, the number of vectors for which Qn is less than T. Okay, so this is should be something like volume of unit ball times determinant Q times the volume of so the volume of the corresponding ellipsoid times radius to the dimension, but okay, I've sort of taken here the value of the quadratic form, so I need to divide by 2. So this is, and it's easy to show that this is 2 up to a power saving. Now the question is, what's a power saving? So if you can show something like that you are equal to this main term up to an error which is little low of you save 1 power of t, then you win. So that's sort of the basic approach, also counting the number of points inside big ellipsoids.
Before you say more about the approach, could you tell us more about the conjecture? Why did it look true? Was there something besides the low dimensional cases, or does this?
You have so the average gap is certainly 0, and sort of why would you expect there to be big gaps though? Not sure I can give much better explanation than that. It's these kind of questions. I mean, already Gauss considered, right? The integer points inside circles, and then Landau. Probably Landau had some relevant work at trying to estimate the number of points. So this is a definite case, and here I can't say much new. So now let's talk about the indefinite case.
This property over here should be only true when you're irrational. This property over here is only true when you're irrational. Or if you have-
Yeah, because otherwise, so this basically implies that this gap goes to zero, and I mean the gap can't go to zero if you only have a discrete set.
The reason I ask is that there's a kind of parallel story with the while law, right? If you have a Laplacian on a domain, then the leading term is the while law, and then the question is when is it big O, when is it little o, and it has something to do with whether the dynamics is chaotic. I don't remember the exact.
Yeah, there's connections, and there's certainly. So in particular, this asymptotic is essentially the while law for a torus, right? I mean somehow. Anyways, let's talk about the indefinite case that I can actually say new things. So if Q is rational, then what I said, Q is rational, then what I said is still true. Then this, I plug in integers, I would get, okay, maybe rational in my sense, I am allowed to multiply this by some constant, but this would be a discrete set. Now, if Q is irrational, it's sort of a bit hard to understand how this set looks like, because problem is Q irrational. It's hard to understand how this set looks like, because big N can have small values for this quadratic form. Indeed, not even zero. Even if the quadratic form is irrational, we still have isotropic vectors. So let's again, there's a difference between d equals 2 and d bigger than 2. So for d equals 2, certainly happens that 0 can be isolated in, even as a multiset in QZ, even if Q is irrational. So for example, you could take Q x y equals x squared minus something like that. And then you can convince yourself that the set of values, okay, so an interesting set of values, but 0 is isolated. Say this way, the minimum or infimum of the value, absolute value of Q of n, where n is a non-zero integer. And this is related to the Markov spectrum. And again, you could say a lot of things about this, but how big the gap is. Interesting story, what gaps are possible, interesting story, but I'm not going to get into the interesting story. And then in the 1930s, Oppenheim conjectured initially for at least 5 variables, but then either he or Davenport or both realized that it should be true even for ternary forms. We have the conjecture of Oppenheim. I think I once looked into it, and my impression was that Oppenheim actually asked this question also for d equals 3. That for d at least 3, if q is irrational, then q of d is dense. The conjecture is no longer a conjecture. The conjecture was proved by Gregory Margulis somewhere in the mid-90s using a completely unexpected technology, using dynamics, homogeneous dynamics. On the one hand, it's completely unexpected. On the other hand, it's in some sense what there are some hints to this approach in the work of Castle and Swinnerton-Dial. Very much surprised, including apparently to Castle and Swinnerton-Dial when Margulis proved it using them. Now, I'm talking about d at least 3 variables, but it's easy to reduce to the ternary case by simply restricting q to a rational subspace. You need to be careful. You need to make sure that the rational subspace you take is such that the form restricted to this rational subspace is still non-degenerate. Okay, but that's sort of something in a code that's not hard to get. And you still want the form restricted to the 3-dimensional space to be not proportional to a rational. But this actually a generic choice would work. If the form restricted to too many subspaces is rational, then it has to be rational to be true. So it's very easy to reduce to the d equals 3 case, which is
You want
in
it
some
to
sense the
still
hardest.
be indefinite. You want to still,
Yeah, that's what they said, but that's a code. That sort of that happens. That's not a generic thing, but that's certainly an open thing. That's definitely something you could guarantee. And in a way, it's similar to what I did here in the definite case. Let's define NQ alpha beta t. So this is the number of integer vectors with the norm of n at most t and q of n between alpha. And so here, in some sense, there's 2 quadratic forms I'm using. One of them is my indefinite quadratic form, but because it's indefinite, to put some order to make sure I look at only finitely many integers at a time, I'm also using the norm, or the norm squared, which is another quadratic form, if you wish. And so the Oppenheim conjecture simply says that for any alpha less than beta, this value is positive eventually for t large enough, but you can wonder how fast it grows. And so this is the collection of integer points inside some shape, right? I mean, there's a ball and there's two sheets of hyperboloids, so it's a nice geometric shape. And if you have some reasonably nice shape and you want to calculate to figure out how many integer points there are, the first guess would be that it should be roughly the volume. So let's let this denote just the volume of the set of vectors. I guess D for me is from now on 3, but I'm not always going to remember to write it as 3. So that's the size of my vector less than T, and Q of V is going to be nothing. The basic guess is that the number of points inside this shape between these quadratic surfaces is going to grow like this volume, which is okay. If you want to precisely calculate, you could do it, but it's sort of slightly annoying. In any case, it's clear what it should be, right? I mean, it's you're taking here a ball of size T, of size radius, sorry, square root of T. So this should behave like some constant depending on Q, and then you have T to the D over 2, but you have this constraint that you want the quadratic form to be between beta and alpha. So you want, and if you take V, a random element of size at most T, then this would also be some kind of distribution between minus T to T. And if you want it to be inside this interval of size beta minus alpha, the reasonable guess would be that the volume would behave something like that, which is correct. This is a correct but I already told you that whenever I can, I will replace D with 3. So basically, it goes like T to the half.
Is this the fundamental difference with dimension 2? In dimension 2, you would just have it be constant as T goes to infinity, so you can't expect to.
No, that's true. Yeah, I mean, basically.
You said it fails in dimension 2.
I failed, and I gave you a complete example, which is an exercise.
So whatever proof you're going to give here shouldn't work in dimension 2.
Whatever, not only shouldn't it work, it would do something which is happened in dimension 2, which is quite important. We'll discuss it. But I'm saying a guess, I didn't state it as a theorem. So obviously, when it's to assume, like I said, obviously we need to assume U is irrational, e.g. if Q is integral, in the naive sense that the coefficients are integers, then I would look how many values, how many integers vectors there are for which Q will be between, let's say, 1/4 and 3/4, for example, it could be many of them. So obviously I want Q to be integral and Q to be not irrational, but that's not enough. And actually, I think the best way to see it is actually to look at the integral case. So you could say this is cheating. There's another problem, which is sort of in some sense more serious. So maybe I'm not going to cheat. I'm going to take Q to be xz minus 1. We'll do something later for notational reasons. I prefer to take twice xz minus y squared, but I mean, that's also good enough for the moment. And let's not cheat. Let's look at the number of values. The sort of best way I know how to not to cheat is to basically maybe take between minus half and a half. Then there's no reason why there won't be integers, and there will be integers. And you could sort of wonder how many things there would be here. So I want x, y, and z to be up to square root of t. So I can choose y square root of t ways. So obviously I'm counting here when I'm saying this is just counting how many integers there are in a ball of size t, for which this is 0. So obviously I can choose y to be whatever I want. It's basically something like e to the half at least, but in fact it's not so far from it. But then once I chose y, I can let x and z to be anything, so the product is going to be y squared. So at least it's a number of average number of ways to factor y. So basically it's something like t to the half log t, which is way more than what should be the main term. And probably an observation of Peter Zarnak, who unfortunately told me he's not able to come today, but it's an observation of Peterson that this can be used by a category argument. So that there are irrational Q for which for some sequence of ti is going to infinity. If I look at the number of values Q attain, the number of vectors, the number of integer solutions to Q alpha between Q of n between alpha and beta, n of size at most t, would be bigger than something like t to the half, maybe to the power minus special. So these so you need to exclude some forms. Not enough to demand that the form be irrational. Okay. So we can. So it would turn out to be essential to exclude forms that are extremely well approximable by rational forms. We'll discuss this in a minute. But even if Q is not, even if Q is not rational, is not very well approximable, or extremely well approximable, I guess extremely is more consistent with notations in the area. Even if Q is not extremely well approximable by rationals, not some kind of invariance. There are problems. There could be.
If you were willing to lose a log factor, would it be? Because the original conjecture just talked about being.
Even if I would just compare, just easy, it's not. But even if I would be just willing to look at a lower bound in the number, I'm not willing to lose. That sort of I'm too greedy. But just lower bounds, no problem. There can always be too many solutions. But if you want an actual asymptotics, you need to make this.
If you want any asymptotics, not the
But if you just want to show that you have at least the expected values, this you could do just by assuming irrationality, that's all you need.
Does this follow from Margulis's proof?
Not from the original proof. It follows. Okay. I'll get both to that question and to Margulis again later. And the answers will be related. But let's but even if Q is not very well, not sort of super well approximated by rational forms, there could be a problem. And what is the problem? So, e.g., you can have integral isotropic vectors. So something like a variant of this example we looked before, xz minus square root 2 of y squared. That's not a rational form. The vector 0, 0, 1 is a null vector for this form. And then if you have a null vector, then just look at how many vectors proportional to it would lie in this set, right? Then just multiples of V would contribute something like the main term. I would contribute, so you can take your, so maybe the vector is null, but you're taking t to go to infinity. So multiples of this vector could contribute something like ordinal times t to the half to this counting. If alpha, let's say 0 less than alpha. So you could have so that's but okay, I mean you could say, okay, I'm not really I'm not counting maybe I don't need to count all vectors, maybe I need to count only primitive vectors. But then that's also, you could maybe have you can have rational two-dimensional subspaces such that Q restricted to this subspace is singular. Maybe something like let me try something. So this is hopefully a form that does not represent 0 non-trivially, but if you look at the subspace x equals 0, which is certainly a rational subspace, your form becomes degenerate. And then this again, if you see just this two-dimensional subspace would contribute something like the main term to our count, and somehow you'd expect that special things, I mean, that the count somehow, this heuristic asymptotic should explain what you don't, understand. If you understand things that add to it, you should expect to have too many points in your counting. So now after explaining all of the difficulties, I can actually state a positive result, which is, okay, the results of Mohammadi, Zhiren Wang, Lei Yang, and myself that I am preparing, that I'm sort of sorry, that I would like to discuss. So let's suppose for simplicity, the term in Q is 1, you could normalize it, I multiply it by scalar, and I'm supposing a very weak definite condition that for every, that there are some constant C and A, such that for every integral from Q prime, so it's basically a n by n integral matrix. So I'm going to take Q minus Q prime, let's normalize it. So now this has determinant 1. I want this to be bigger than C times the determinant of this quadratic form. Okay, that's sort of a, or maybe norm, let's say norm. Okay, this is a relatively weak assumption. Satisfied, for instance, if my, so you wonder how should I verify such a thing? So just by sort of trivial Liouville type bounds, you could just hold this Q has entries that are algebraic numbers, but it's still irrational. Right, so something like this quadratic form would satisfy this condition. So this is my definite condition Q. And then under this assumption, so Wu and Kim, building on work by Eskin, Margulis, and Moses, and work of Danny Margulis, showed that if 0 is not inside my interval,
Big trouble with the assumption, it's scaling right on the left, not scaling it on the right.
yeah, it's like asking that alpha minus p over q is bigger than c q minus o. Hey, right? I mean, sort of, it's always you take. So here I'm approximating in some projective space. This is just somehow the. I could have written distance in a projective space or something. But it's a natural thing to do. I mean, it's obviously. So under these conditions, this is a very recent result, actually, the result of Kim. Eskin, I'll talk about in a minute, showed that this is actually asymptotically the number of solutions to my system of inequalities goes according to the expected mean term. So Wu and Kim basically graduated this year. I don't really know if you already defended this thesis or not. The technology was developed by, so basically Danny Margulis, first proved asymptotic lower bound, that you have at least the right number of solutions. That is to say that the number of solutions is at least 1 minus little of 1. This is little of volume. And then Eskin Margulis models, depending on how much time I have, I was hoping to explain how this is done. Proved it basically for Q of any signature. Except one thing. So basically they proved it, let's say this way, they proved it for Q of signature 2,2. Where you need an whiskey fountain condition, which is needed, and any signature PQ, well, I guess P is bigger than 0, Q is bigger than or equal to 0. So this covers all cases. In that case, there's no Diophantine assumptions needed. And it's sort of, there's something hidden in this, the way I've stated the result. I sort of explained to you that it's not this charted Diophantine assumption is not enough, and I stand behind my explanation. But when I was explaining to you why it's not enough, I gave you examples where you have too many solutions, where 0 is for which the value of Q is equal to 0. We do not care about error terms. That's sort of the only thing you have to be careful about. Okay, but now let me state our theorem, and then I sort of try to do some damage control and see how much I can explain to you about either what we do or what Eskin, one of these people, Wu and Kim, Eskin, Margulis, modest Danny Margulis did. But let me state the theorem, because I think there's something interesting here. What's the statement? Some new phenomenology that you don't see, at least not severely, if you don't look at things quantitatively. So alpha less than beta, any Q definite. Ternary quadratic form. PA not stringly well approximable. For some C and A in this particular sense, then you have some constants, the most interesting of which is kappa. If or maybe I'll write it this way. So you can write the number of integer solutions as the volume plus some power saving term with this exponent. And okay, I want things to be able to change all of the parameters, so maybe I'll add here beta plus alpha plus 1 to the power n. Okay, so this is something which basically wants to force alpha and beta not to be too large. And plus some remainder term. And what is this remainder term? So the remainder term exactly accounts and most for one-dimensional rational subspaces. So basically, right things spanned by a rational vector L1 to L4. And at most for two-dimensional rational subspaces P1 to P4 such that I'm not so Q is I need to add a bit more epsilon deltas to explain what I mean, but say it's almost isotropic on L1 to L4. So in particular, if you need some, if you don't have this, if you're not within this error term, it's sort of forces you to have either almost isotropic vectors or what would amount to almost isotropic vectors in a dual quadratic form. And almost degenerate P1, P4. So it's basically saying that P1 to P4 essentially by duality correspond to some almost isotropic vectors in the dual in some dual form. And R, this remainder term, is simply the number of relevant vectors in this region, in the region on these at most 4 lines and 4. And it just exists. You can't. It's not that it's sort of a limitation of the technique or something. I mean, that basically I showed you how to create forms where you would have this error term. It actually exists. It's sort of not something. You might hope for some magical cancellation, but in fact, the theorem tells that there is no magical cancellation. And the corollary is that if Q is indefinite, irrational, and the algebraic entries, there is a kappa which depends, I guess, on the algebraic, on the degree of the algebraic numbers, is if you want to do things effectively. Such that if I just exclude, so this is a number of points in some variety, so that Q of my vector is inside alpha beta, but is not equal to 0. So I'm just excluding the 0 vectors. Would be what you'd expect by the volume up to power 7, up to some constant, what alpha beta to that. Some number again depending on various arithmetic data that into the half. Okay, so if you have formed algebraic numbers, you have sort of a nice clean statement. But if you actually want to see how it's proved, it's actually proved by saying that if I had a mismatch between these counts, this would produce almost isotropic vectors, but sort of the almost isotropic is so strong that it would somehow force the almost isotropic vectors to be actually isotropic. And then the value of the quadratic form would be zero. So somehow the corollary is quite simple, but it sort of hides what is actually going on. So now let's see how much I can explain about relation to dynamics. So what is easy to explain, I'll start with that, is explain how Margulis proved the Oppenheim conjecture. And maybe I'll sort of the dynamical ingredient I'll show is a bit stronger than what Margulis had. It's something you obtain later with Danny. So I will give you so here's relation to dynamics. So we switch point of view. So instead of looking at a fixed form, and then I'm looking at the values of Q in ZD, D equals 3, I'm going to look at, sorry, not fixed, a variable form, but somebody give me a form. And I'm looking at its value in a fixed lattice. I'm going to basically write Q as Q0 both with some element G. So if Q had determinant 1 and Q0, if my fixed form had determinant 1, G would be an element inside S3 R. So for Q0, I can take basically there's only up to sign, right? I mean, I can assume the signature of my form Q is 1, 2. And I have a favorite quadratic form, irrational, maybe you have a different one, but I have a favorite irrational quadratic form. I'm going to choose it. Why not? And it has determinant 1. So I can write this quadratic form, irrational quadratic form that you gave me as my irrational form composed with some element that implicitly you gave me in S3R, and then I can look at the value of Q0, not at the integer lattice, but at some other lattice. This is, I'm looking at, instead of the variable being which quadratic form, I'm taking the variable is going to be on which lattice I am evaluating my fixed quadratic. And so this point, G is 3 is a point, is sort of a point in the space of unit volume lattices in R3, which I can think of being SL3 R modulo SL3 Z. And it doesn't seem like I did much, but here is sort of the point. This and here is why where 2 and 3 are different. So this form has a large stabilizer. Is a large group. It's basically it's locally isomorphic to. It's basically isomorphic to EGL to R. Right? I mean, it's has point this one parameter group preserves my quadratic form. This one parameter group preserves my quadratic form. This is easy to see, right? Because if I multiply x by e to the p and I multiply z by e to the minus t, I haven't changed the form. This is a bit trickier to do some cancellation, but this is also true as well as and I mean these groups together generate a symmetry, but there's sort of a big group of symmetries. If I choose a two-dimensional case, there would also be a non-compact group of symmetries, but this group of symmetries would be much smaller. It would just be a one diagonal group. Here it's sort of a much bigger group, a reductive group with some an honest semi-symmetry group, a big group. And if you and the point is that if you don't like the given lambda, you're free to evaluate. If you want to study the original Oppenheim problem, you're free to evaluate Q0 on H lambda for any in the symmetry group of Q0. Now, what Daniel and Margulis proved, strengthening something that was earlier result of Margulis, what Daniel and Margulis proved is that in SL3R modulo SL3D, any H orbit is either periodic or it's dense. So if it's periodic, this is a dynamical statement. It was proved using techniques of topological dynamics. But if you think about it for a minute, so if I have Hx is periodic, means that there are sort of many, so I can look, so there are many gammas and H's in SO Q0 such that Hg is equal to G gamma. If you think what this means, i.e. many gammas inside SL3V, such that if you take my original form Q composed with gamma is equal to Q. So I have here, so my quadratic form has to satisfy a lot of integer linear equations. If you have a lot of integer linear equations, then you could hope that if there are enough equations, basically Q has to be on a rational subspace. So this means that Q is rational. So if I start with you gave me a quadratic form. I wrote it as Q0 times G, but okay, I could do it in many ways. I did it in one way. Then I'm saying I had this degree of freedom of multiplying by any element of the symmetry group of my quadratic form I wanted. If this didn't give me a lot of freedom, I'm sort of trapped in a periodic H orbit, then this is a way of convincing myself that the original quadratic form you gave me was proportional to integral. If it's not periodic, it's dense, and basically inside X and lambda are the same, just sort of When I think of it as a lattice, I write it lambda. When I think of it as a point, I write it x. Sort of same thing. Yes, it should be. So if H lambda is dense, then Q0, if you look at the value we attain, contains basically any value Q0 can attain on any lattice. If I wanted to engineer a lattice so that Q0, so that it would have a vector, so that Q0 on this vector would be equal to 3, that's obviously how to do it. There's no restriction. So that's sort of how, so that's how Daniel Margulis proved it. And I would give a slide. The slide is of hints how Daniel Margulis and later this was sort of got the lower bound and later asking Margulis models, and we and King were able to get an asymptotic. And this is the following. So this is the theorem of Shah, but basically, I think he will be the first to say that basically the key input is the landmark work of Ratner. So what Nimish has shown is a distribution statement. So same, let's say same setup, or more generally, whenever you have basically whenever I have a unipotent element of a semi-simple group, so I can look at some, take F to be some nice, take F to be continuous function of G mod X, bounded, loosen the bounded a bit, but not very much. And I'm going to take integral between 0 and 1 of F over an orbit of this unipotent group, this group here, particular group here. But then I'm going to apply a big element 80, which sort of makes this, if you think about it, this thing would be the same thing as the integral from 0 to e to the t of F US 80x ds. So this integral of size 1 is secretly a very big integral. It's a big one. Goes to the average of F from G mod gamma less Hx is periodic. So obviously this is a stronger statement than the statement of Daniel Margulis, because it just doesn't just say that this orbit of Hx is periodic. It says that this particular sequence of one parameter things are not just dense, but they are actually equidistributed. And this equidistribution, I mean, you could basically you could present this counting, you could present this kind of number of, I'm lying here, but only a bit, as essentially maybe vectors v between t half and t. You could present it, so maybe it's slightly, I'm just taking vectors of some given size. You could write it as some this kind of average that Shah considered, where F is positive, continuous, small error that you can control. Positive continuous, but not bounded.
X.
Not bounded.
X should be generic or something. So
X is the quotient of G, and G is the thing which brings your given quadratic form to.
for every X for which it's not real. I guess I missed the line. But okay.
No, this is
true for every.
This is true,
Which the-
this is always true, that this number you could write essentially as this type of integral. Q per Q, X periodic, not periodic, you could write it this way, but of course, you could apply Nimisch's theorem and say this converges to the integral of f over the whole thing, which will give you the contribution of the volume, only if this point is not bounded, and the key, so Danny and Margulis, what they did was, okay, we'll just chop f very brutally, we're not changing the integral very much. F is not bounded but integral, but and finite integral. So what Danny and Margulis did, we just use positivity to get lower bound. Eskin, Margulis, Moses, Wu and Kim were fighting this unboundedness of f, and they had to exclude some orbits because this otherwise the theorem would be false. And what we did, the key engine that we inputted is an effective form of the theorem. We showed that this converges to this exponentially fast, unless you could say something quite significant about your starting. And I guess that's all I have time for.
Are there any quick questions?
The assumption that you're not close to an integral, to an integral form, does it enter into the effective form of this theorem? But is that something you input?
Yeah, so there are two things. I mean, if you are very close to periodic orbit of, in an effective world, if you are close to some periodic orbit, very, very close, you can distinguish between being on this periodic orbit and being very, very close. So any kind of effective statement of this type would basically also say that either you are close to an integral or you could find a nearby periodic orbit. Being very close to a periodic orbit is also bad because it sort of makes it hard for you to control the amount of time you spend where f is very large. So it's sort of used in both of these places.
All right, well, let's thank everyone again.